Hello, today we're going to work on lesson 3, which is called orbital notation. Orbital notation actually builds on the foundation that we established with electron configuration. So I would like to actually begin today's lesson by sharing a few things about the electron configuration homework. So if you look behind me, begin today's lesson by actually looking back at the electron configuration homework. There are a few things that I noticed when grading assignments that I want to point out to you. Number one, when you are writing the full electron configuration, please make sure that if you have a D sublevel, that it comes after the 4S sublevel. I know on some websites, if you go to look up answers, you'll see the 3D10 right after the 3P6. This is wrong. It should not appear that way, and that is not the way electrons fill into that orbital. So what I'm reminding you is that we will write the 4s2 followed by the 3d10 and then jump back to our 4p6. When I looked at the answers for some of us for the noble gas configuration, one of the things that I noticed was that some of you are jumping past the noble gas and only including the last piece, so the 3p1 or the 4p5. Please know, you cannot jump to right before your last one. You can only jump ahead to a noble gas. So for example, if I'm looking at tin, I can't jump to 4d10, which would be silver. Instead, I can only jump to krypton and then continue from there. 5s2, 4d10, 5p2. So I started off this lesson by saying that electron configuration is the foundation for what we're going to be doing for the next 2 lessons. So once we learn electron configuration, today we're going to move into orbital notation, and that will leave quantum numbers and Bohr diagrams for us. Now, with each of these, knowing how to write the electron configuration is a cornerstone in getting either of these or any of them correct. So let's take a look at orbital notation. Behind me is a picture of an orbital notation diagram for the element germanium. It says, orbital notation is a depiction of how electrons occupy atomic orbitals in order of increasing energy. Now, if you think back to when we looked at Bohr and the solar system model, this is just an expansion on the solar system model. For example, if I'm looking here at the 1s sublevel, imagine that circle coming right through where this sublevel is. And the second energy level would look like this, and the third energy level would look like this. So we're essentially targeting, zeroing in on specific energy levels in that Bohr model for the atom. When we keep going, you'll notice that the number of sublevels also increases, and that is occurring because as we go higher and higher and further away from the nucleus, we start introducing the P sublevel, the D sublevel, and eventually the F sublevel. There are some terms that I will be using that I want to make sure you are familiar with before you watch the rest of this video. So first of all, the first term is energy level. Energy level refers to that large number that's out in front in our electron configuration. So if we're talking about 2p6, this part is our energy level. The second part is the name for our sublevel, sometimes called a subshell. So a sublevel is either S, P, D, or F. So in this example, the P is our sublevel. The last piece that I would like to talk about is the orbital. So depending on what sublevel you are in, you have one or more orbitals. So if you are in the S sublevel, notice all of my S's here have just one box or one orbital. If I'm in the P sublevel, notice that my P sublevels consist of 3 boxes or 3 orbitals. Finally, my d sublevel consists of 5 orbitals. Each orbital is capable of holding 2 electrons. So, if you notice, the highest number we will ever have for an s is s2. When we have p's, the highest number that we'll ever have in the p sublevel is 6. And because we have 5 orbitals in the d sublevel, the highest number of electrons we will ever see in the d sublevel is 10. There are 3 basic rules that we must know in order to appropriately place electrons in an orbital notation diagram. The first of these is called the Aufbau principle. It says that the Aufbau principle states that an electron will occupy the lowest energy orbital that will receive it. So here again, we have our orbital notation. Think about the bottom here as our nucleus. This is the lowest energy orbital. And as we get further away from the nucleus, we get higher in energy. So this is the highest energy orbitals in this particular example. When we are filling electrons in, we will always start at the bottom, closest to the nucleus, and work our way up toward the top. The second rule that we're going to talk about is called Hund's rule. Now, Hund's rule states that orbitals of equal energy are each occupied by 1 electron before any orbital is occupied by a second electron. And all electrons that appear in an orbital with just 1 must be pointed in the same direction. Now, the easiest way to think about this rule is to consider Thanksgiving. Imagine you're sitting at a large Thanksgiving dinner with your extended family, and the mashed potatoes come to you. You scoop out some mashed potatoes, you pass it on to the next person. You will not get a second opportunity for those mashed potatoes until everyone at the table has had their chance to get one. That is exactly what happens here. No electron will occupy an orbital before each of the orbitals that are equal in energy each get 1. So I have 3 examples along the bottom here. Let's talk about why the first 2 are incorrect and the third one is correct. So first of all, if you notice, the second part of this statement says all electrons in singly occupied, that means with just 1 electron, orbitals must have the same spin. So because these 2 are pointing up and this one is pointing down, this is a wrong answer. Notice that in the correct answer, all 3 electrons are pointing in the same direction. The second example is wrong because of the first part of the rule. This orbital has 2 electrons, but this one has none. That's like you taking seconds at Thanksgiving on those mashed potatoes before someone at the table had their chance to get the first scoop. So again, this model is wrong because of this electron. The last electron obeys both parts of this rule. All of the electrons are pointing in the same direction, and each orbital has received 1, and none, in this case, have received 2 yet. The third rule that we'll have to follow is known as the Pauli exclusion principle. It states that no 2 electrons in the same atom can be placed in the same orbital spinning in the same direction. So imagine if you have an orbital and you have 2 electrons that are in it, they have to spin in opposite directions. This, where both electrons are rotating the same way, would not be permissible. So if you look at our first example over here, we have an orbital that has 2 electrons in it. They're both pointed up. We cannot have that. Here, if we add 2p4 and we're placing electrons, this would work out because 1 electron is pointed up. Then we went with our second electron, our third electron, and then when we add our 4th electron, we make sure that that's pointing in the opposite direction. So let's take a look at our first example, which is nickel. With nickel, what we're going to do is begin by looking at the electron configuration. Now, when you attempt your homework assignment is based on some of the examples that we have already done. So you're going to be able to go back and look at your electron configurations for the electron configuration homework and use those to complete your orbital notation homework. So for nickel, we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d8. So now, knowing that each arrow represents one electron, we're going to go sublevel by sublevel till we get to the end. So in the 1s sublevel, we have 2 electrons. One must point up, one must point down. In the 2s sublevel, we have 2 electrons. One must point up, one points down. In the 2p sublevel, we have 6 electrons. So according to Hund's rule, up, 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 followed by down, 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 till we get to 6. 3s2 means 1 up, 1 down. 3p6, 1, 2, 3, 4, 5, 6. 4s2, that means 1 points up, 1 points down. And then 3d8. So we're going to start always going up first. 1, 2, 3, 4, 5, 6, 7, 8. I picked silver as our second example because it's one of our exceptions to the rule. So if you have an example like silver, remember that when you're writing the electron configuration out, we change what we expect in order to get our, in this case, completely filled sublevel. So we have 4s2, 3d10, 4p6, and we wind up with 5s1, 4d10. So filling in our electrons, we have 2 in the 1s, 2 in the 2s, 6 in the 2p sublevel. So we're going to put 6 in here. 2 in the 3s, 6 in the 3p, 4 in the 2s, 10 in the 3d. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In the 4p, we have 6. In the 5s, we have 1. And then in the 4d, we have 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Notice the exception is right here. Instead of this having 2 electrons, that electron has been promoted and is now over here. Let's take a look at example number 3. For aluminum, this one's a lot shorter. So aluminum, we have 1s2, 2s2, 2p6, 3s2, 3p1. So 2 electrons in the 1s, 2 electrons in the 2s, 6 electrons in the 2p, 2 electrons in the 3s, and finally 1 electron in the 3p. We are now looking at the homework assignment on orbital notation. Let's take a look at this first example, which is for manganese. So the very first thing that I would do is look up the electron configuration for manganese. Now, your electron configurations for the examples that you will be doing are already completed as part of the electron configuration homework. So I'm quickly going to jot down the electron configuration for manganese, which is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d5. Now, with that in mind, I'm going to go ahead and double-click on this diagram. That will open up a picture that looks like this. These electrons are already included in your picture. So the first thing that you want to do is make a bunch of copies of each of these electrons. To do that, click on the electron, press Control-C to copy it, and then Control-V to paste it a bunch of times. If you need more, you can always make more copies. Do the same thing for the down pointing electron. Now, once you have a bunch of up and down electrons, you can begin placing them into the orbitals. So 1s2 would have 2 electrons in it. 2s2 would have 2 electrons in it, one pointing up, one pointing down. 2p would have 6 electrons in it. So you're going to have 3 that are pointing up first, and then 3 that are pointing down. For the 3s, you'll have 1 pointing up, 1 pointing down. For the 3p, again, you'll have 3 that are pointing up, and 3 that are pointing down. For the 4s, you'll have 1 that's pointing up and 1 pointing down. And finally, for the 3d, you're going to need 3 that are pointing up. You'll need 5 that are pointing up and none that are pointing down. You'll notice that it is half filled. You can go ahead and delete any extra electrons that you have. To save this, hit Save and Close. If the Save and Close button is not visible, you might also have to zoom out of your screen. So the first one is now completed for you. If you have any questions, please feel free to send me an email or message me through Schoology. I hope to see some of you at office hours this week. Thank you, everyone. Have a great week.